Let's talk about today's topic. Today we're going to talk about view change protocols and reconfigurations. And mainly we're going to talk about this lady, Barbara Liskov, and we're going to cover this paper, which is view stamp replication, a new primary copy method to support highly available distributed systems. I really encourage you to check her profile, okay, to read her wiki page. She's really one of, I mean, we have a lot of successful women in computer science, but there are still, the number is much lower than the men. So if you want to stay motivated, especially for the ladies in the class, she's the one who can check her profile and see how successful she was. So we're going to talk about this paper, about basically talking about replication in a more extended manner. It was like first or second week we talked about basically primary backup replications in the class. You remember we talked about that example of a bank wants to have a replicated basically database in another city. So we wanted to have to basically copy it. And we discussed it, but in a very, very brief manner. But today I'm going to talk about it more. Okay. Okay, that's the original paper in 1998. Okay, it's so she had basically published another paper in 2012, if I'm not mistaken. So she basically went through her own idea and basically revised it and rediscussed it with a more like a modern. I mean, because from 1988 to 2012, if I'm not mistaken, a lot of changes happened in computer science. So basically, she revised it after all those years, and she revisited it. So this is much, I think, a paper that makes much more sense reading it, okay, because it's much more recent compared to the one in 1988. So before we discuss the today class, I received this comment last week, okay, about the assignment being redundant. Okay, so let's do something else with the assignment. So I want to discuss with you what I'm expecting you to do. Maybe you find it easier citing, or maybe some of you find it a little bit harder than talking about the class topic. And it's just I came up with this idea. Maybe something interesting can come out of it. So I'm not going to put what I'm going to say now in the descriptions because it's lengthy. So you have this recorded version. Now I'm talking to you about what I'm expecting. Then I just, in the assignment 2, in the description, I just say the title and this is the deadline, okay? So please pay attention what I want you to do. Basically, the whole idea is I want you to read a paper on your choice, okay, about like a new paper on your choice in the distributed systems area. And I want you to summarize the paper and write like a maximum 1-page summary of the paper. Discussing the paper, discussing the idea, talking about advantages if they have, you detect some disadvantages in their approach, and like discussing it, like basically reviewing it in a very brief manner, not more than 1 page. Okay, it can be, yeah, somewhere between half page and 1 page. Okay, so I want you to go to basically Scopus, okay, and search a paper. I'm discussing this because I want the paper to be in a certain, basically from certain time, not certain journals, but not any papers that you can find. Let me just, I don't know, I have to sign it. So I want you to do basically systems. I want you to search about like machine learning, okay? So distributed system machine learning, or you can, if you're wishing to, you can maybe add distributed computing. Okay. And search it. So you're going to find a lot of papers, okay, in this area. But then I want you to limit the topics to last 3 years. And also just the journal articles. So I want you to basically read the last 3 years papers, or like from 2017 to 2020, because there are most of them are in this years. So just journal articles, okay, and then you can look for it in this way. So you find a lot of papers. Most probably is again because if you see here, I put distributed systems, machine learning, distributed computing, and I set it so they can check that basically keywords in title, abstract, and the keywords, okay, in the papers. But please make sure that they are related, okay, and choose a paper of your choice, and prepare a one-page summary of the paper. So which paper you're choosing is totally on your choice, okay? But try to find something like this is what I was doing actually. Like I did a quick search on Google Scholar, like to see. I didn't say Google Scholar because there would be a lot of papers from a lot of other resources that they might be not so reliable. But when you limit it to the Scopus, so you get it basically mainly from journals, like reputable journals, mostly some conference, as you see. But what I'm expecting is just the journal papers, okay? Papers that published in journals. So, like for example, this is what I searched in like Google Scholar. You can see there are like, for example, large-scale machine learning on heterogeneous distributed systems. Sounds super interesting. So topics like this, okay? For example, a distributed system for pattern recognition in machine learning. I mean, I'm showing you to see what type of basically idea you can get there. Go ahead, Paul. You wanted to ask something?
Yeah. So okay, only to be sure that I'm understanding that we're understanding correctly, yeah. Is that we are going to select only one. We are going to look for a paper that it's related to machine learning and also to distributed systems, and we are going to make a summary of that.
Yes, that's it.
Okay.
But the paper should be from a journal paper, okay? I mean, what I'm like, I expect you to maybe you can just look for IEEE journal, IEEE transaction journals, or I mean, try to see it from like from which journal you're basically picking up. Okay, for example, their transactions are way more reputable than a lot of other journals. Okay, so you can consider that as well. Where are you getting here? What I did I sorted by citation. So the more citation means the more reputable is the paper itself. Okay, so you may not do that. Okay, if you don't wish to, you may look for the newest one. But it would be good that choosing a paper that has a really good number of citations. Okay, not necessarily like the biggest one, because if you pick the biggest one, most really it's going to be from 2017 to 2018. So you can put it or basically sort it by the date, finding some recent papers from maybe Journal of Cloud Computing. It sounds like very much related to this area of distributed computers. And finding something like see, the whole idea is like for you to see what's happening. Okay, talking about like machine learning, something as a hot topic, and distributed system as something very fundamental and like something very, I don't know how to say that. some classic topics, maybe like with those classic issues that we're discussing now during these classes. So seeing what's happening there, okay? And then I will share all the summaries with everyone. Okay, the same thing that we did with the previous basically assignments, but this time it's just a one-page summary. I'm going to change the grading, okay, because it wasn't that fair the last time. So then you will be having access to all the summaries, so it can be a really nice source also for you to see, to go through a lot of summaries and see what's happening without going to reading all the papers just by yourself. Go ahead, Antonio.
Yeah, that was my question. I mean, is it going to be peer-reviewed?
I would put peer review, but I wouldn't do that same grading style. Okay.
A question
Questions?
about a Scopus page.
Okay.
If we make an account in that page, that content will be available for free?
I believe so. I mean, I sign in with my tech account. So I think you can do the same thing with your tech student ID. Ah, okay, that's the issue. Okay, wait. Yeah, because no, the thing is, if, for example, you click this papers, you're not going to have access to it because some of them are not open access. If I download, let me see if I can do that.
Well,
No.
but there are also databases that we have access through the library of Tec de Monterrey, right?
Yes, that's. I mean, I don't know. You for using that, you need to have like a VPN because you are not inside the tech and you're not using tech IP address. So I don't think you can have access outside tech. Okay.
Okay.
Okay. So for that reason, maybe it would be makes sense to look it for in the Google Scholar, if you're wishing to. Okay. The same thing, you can do that. You can limit the years here. Just find the recent papers. Okay. You can also do the same thing here. Put your custom branch, sort it by even like you can consider the citation number. And the good things here is Google Scholar tells you if the paper is available in other sources in a PDF format. And us as a researchers, we try to do that. I mean, I'm not just, when I publish a paper, I'm not just putting it in the journal. I try to, for example, upload an unformatted version in somewhere that everyone can access for free. Okay. I mean, don't discuss the ethics of that with me, but that's what we do. So that's why you can see most of the papers are available in some other part, in other journals, in other basically websites. For example, this is published in IEEE transactions, but it's available on archive too. So you can have access to the PDF file. So usually these are preprint or unformatted version of the same paper in the journal, but they are the same content. Any questions? So yeah, maybe you can do that in a Google Scholar. So to make sure that you have access to the file.
I have another question.
Go ahead.
Shall we include our name, or this should be also anonymously when uploading the file in Canvas?
Yeah, keep it anonymous. Anonymous is better.
Okay.
Because that gives us more options to play around with it. Okay.
Okay.
And it's just something I was just thinking about basically this assignments, about the comment that what can be like interesting assignment, not also too much work. I think that's a good practice. I thought that can be a good practice also for you to see how you can do research on your own. Finding the papers, finding the resource, making sure it's a nice paper, is from maybe even what you can do here, for example, just maybe I'm going out of topic a little bit, to make sure who are the key authors in this area. Maybe you can go and look at basically the authors, like for example, the authors, okay? So you can see, for example, this author has, Booyah has like 36 papers just in this area using these keywords in the last like 3-4 years. So then you can basically somehow detect the key researchers in the area, and then maybe you want to look for those papers from basically those key people in the area, because they are the one basically pushing the boundaries. Okay, they are the one like most active in this area. So I thought it can be good practice for you to do the research and also to read more than just one paper that you're presenting. Okay, because I'm pretty sure no one reading all the 11 papers that we assigned.
So we are going to in the paper, in part of the summary is going to be the source of the paper.
Yeah. You basically what you do is you cite the papers. Okay, like let me show you again. Like if you find it here, for example, okay, for example you want to use this paper, just an idea, you can put like a which one can be, or like one of this citation, whatever you're preparing, okay? You can include like Vancouver style or APA style citation of the papers that you're using. So here it has a date, journal, and basically the title of the papers and the authors. So you can put on the top of the papers the name of basically the citation of the papers, and then the summary. That's it. As I mentioned, no more than one page. No more than one page, but not just like 5 lines too. Okay, like something we feel like sometimes I have to be so specific, like more than half a page, less than 2 pages. It means like in 1 page, fit in 1 page. I'm sorry. I mean, sometimes like you say, oh, you didn't mention it can be like 2 lines maybe. I mean, a summary. I think. That's how you can do the summary of the paper, that maybe you can look for some, no, I don't want to say that, that gives you a shortcut to do it. Just read the papers and summarize it. Okay? Is that fine?
It should be a formal writing or just an informal, or should we follow some guidelines or?
No, like try to like do the academic writing.
Free format? Okay, thank you.
Yeah, just not like casual writing, but like a official academic writing. And I'm pretty sure when you read the paper, then you see how you can write. But just make sure you're summarizing, not copying like the abstract and putting it in the summary, okay? Because it will be automatically checked for basically plagiarism. Not just abstract, putting there or like rephrasing the abstract. No, really go through it, and I think you will find it interesting if you're interested in machine learning, you're interested in this topic, see what's happening in the latest literature about distributed system. Because whenever we were talking about like the main issues with the distributed system. You see, the paper I'm talking about to you today is from 1988. Okay, so you might find it, what the heck we should talk about a paper from 1988. So what we are discussing is mainly the very fundamental issues, which are mostly already solved. Okay, of course it's not like there is no more research on those topics, but mostly are settled, those things. So more maybe we're moving towards the applications oriented research, like what we can do with what we have now. Okay, we're talking about AI, artificial intelligence, machine learning. We have this basically this distributed system, what we can do and achieve using them. Okay, so that's the idea. Clear?
Yep.
Sure.
When will be the due date?
The due date will be the due date will be like okay, good question. Because if you put the due date long, then there would be short time for how to say, for peer evaluations. So the due date, let's set the due date for next week, Friday. Okay, so basically for next week, Friday, which will be October 9. No, October 16. Okay.
Okay.
I'll put that here so I don't remember. I don't forget. 16. So October 16, it will be nice. Like you have already some, basically tomorrow, because you didn't finish late. Tomorrow till basically 8 more days to do that. So it's all about basically reading a paper, because writing a page doesn't really, it's not a difficult thing. Okay, let's continue. More questions, or shall we continue? Okay, I hope it's clear. If it's not clear, so we can discuss it. So let's do. So this is the outline of today's discussion. Okay, it's very whatever I'm going to discuss today is really like rational. There is nothing really hard about it. So we're going to talk about primary backup replications. We discussed about this a little bit from very beginning of the class, but if you remember, we put a lot of conditions. There is no failure, packets arrive without any problem. So we make it, we simplify the problem a lot. So today we're going to basically put all those real conditions in and discuss what would happen. Then we're going to talk about view change protocols and the configuration. So let's start talking about replicated state machine via primary backup. This is what we discussed from using this example. If you remember, the bank that is in, I don't know, New York, want to have another branch in San Francisco. That was what we were discussing. But so what we did there was basically stateful server replication for fault tolerance. Okay, so what we did there, we said, okay, we have like a bank and another bank, and we want to have another replicate of the same database in another locations. So in case one of them fail, system doesn't fail completely, so it can keep operating. So basically, a stateful server. Talking about this stateful server means like it remembers basically client or the user data, okay, from one request to another, one transaction to another. Let's say it remembers that. That's what it means by stateful. Okay, don't get confused with the name. So this was what we discussed, okay, and so we had basically these replications. Okay, remember we had one replication in another location, but whatever we discussed those days was no network failure, no packet missing, everything was working perfectly, all the packet was arriving to the backup. So we used that totally ordered multicast to basically to implement this. It's basically what we can call it like primary backup replications. So we had a primary, we had a backup, and that's how we make the system fault tolerant somehow. So, but what we didn't discuss from the beginning was we didn't discuss anything about a replacement, server replacement, the failure of the server. What would happen if one of the server fails? We didn't discuss anything. What would happen if the packages doesn't arrive on time, or broken packets out of order? We didn't discuss any of those issues. But we're going to discuss those today. I mean, mainly discussing about replacement, server replacement, and basically server failure, and how we can deal with those situations. So basically what we want to do that, we want to make these stateful servers fault tolerant, really fault tolerant, not assuming they wouldn't basically fail. So we discussed about eventual consistency, and in eventual consistency we have a multi-master. If you remember, like in the case of Amazon Dynamo that we were discussing for a high availability, So any node in those examples would accept the operations. If you remember, we said we're going to have conflict at some point, but we do something with the conflict later. But let's make the system very much available, and let's all node accept basically operations in that. So we can call that a like multi-master basically system that you don't have just one master, one backup. So the master only accepts the operations. That was not the case there. So most of the nodes, or any nodes could accept those operations. And then basically it was a asynchronous system because node would synchronize the state after the operations, like what exactly we see in like last week Amazon Dynamo. But eventual consistency is not always great. You remember last time there was a comment that, so if this is so perfect, like everything sounds so perfect for Amazon Dynamo. Okay, but we know that it is following this eventual consistency, and eventual consistency isn't appropriate for all sorts of applications. So for example, imagine an eventually consistent file system that each time you're revisiting the file, you would see different content. The content would vary, which is not something basically not something that we look for, like an eventual consistent file system. Or in a network file system, clients can read, write to different masters, see different versions of files, which is not, again, something suitable always. And the point is, a strong consistency makes application easier to write. When we don't have that eventual consistency, and like all the nodes can accept the operations, and then we do something with basically we synchronize operation later, and we somehow deal with the conflict that comes up in the system. That makes a write operation difficult. In contrast, when we have a strong consistency, let's say we have that in that example, one basically primary, one another replica as a backup. So we just write the operations in the primary, and then the primary synchronized with the backup. So in that case, the system would be basically the consistency would be much stronger than eventual. So this was basically the idea with the primary backup replications. So the mechanism is that we replicate and separate services. So we have a client, we have a primary that is constantly in touch with the client. Client basically do all the operation with the primary, and the primary basically replicate those states in the backup system. So this one is basically the goal for primary backup replication is reliable despite individual server failure. In this type of system, these are our goals. And another one is this, it gives a semantic of a single server for the client. Client doesn't know what's happening behind the scenes. It's like always feeling that the client is talking to one server. And of course, it's somehow basically reliable despite individual server failure. If the primary fails in this case, backup would just replace the primary and everything would smoothly work. So the operation is like basically you nominate one of the replica. You have like two replica. You nominate one of them as a primary and other replica as a backup. So only one primary at the time. We have only one primary at a time. This example, and clients send all the operations to current primary, and primary orders clients operations. And then basically all this ordered operation will be passed to the backup. So the state of primary and backup would be the same always. So in this case, we need to keep client, primary, and backup in synchronization. So basically, client needs to know also who is primary and who is backup, right? Because clients are always talking to the primary, not to the backup. So it's very sensible things. It's very easy to understand this primary backup replications. So talking about basically a state machine. we can see any, like, for example, a database also is essentially a state machine, because all those values stored in a database, like key value pairs, you can look at them as a state, okay? And the operation that's happening in that basically database can be like a transition between different states, going from this state with that to that state. And I mean, I'm setting this assumption here, or this definitions here, so later you don't get confused. So key assumption here are operations are deterministic. This is very important. So there is no basically randomness in the operations, okay? So basically, you know what the state would be after each operations because it's a deterministic operation. There is no randomness involved, okay? And why we put this assumption, okay? This is key assumption is because if the operation is deterministic, then replica will end in the same state, because there is no randomness involved in primary nor in the backup, because the operations are deterministic. So basically, they will end at the same state after finishing the basically the operations. So another example, another things here is as consideration is each operation executed on all replica or none at all. Because if I execute that operations in a primary, not in a backup, they're going to end up in two different states. They're not going to be identical to each other. So either, if, for example, in that case, if the backup is dead, primary cannot execute the operations. Because if it execute, the backup would come, that basically there would be some missing operation there. For example, the primary running, working, backup is failing, and then the backup is coming alive, primary is dying. So there would be some state they're missing. So that's why either they execute all of them, all the basically replicas execute that, or none of them at all. So we need this distributed all or nothing atomicity in this consideration. So there, you can refer to this paper for more reading about what basically we discuss about this fault tolerance, achieving fault tolerance using the state machine approach. It's a tutorial paper. It's like easy to follow if you are interested. And from 1990. Okay. So let's discuss it. What happens here? The simple basically operations. And let's look at basically trace this steps for each operation. So operation here is we want to put value 1, okay, integer 1 into variable x. So it's try and send the basically comments. Okay, primary gets operations, primary orders operations into its log, and then it replicates the log of operation to the backup. So it sends basically those replicated log to the backup, and backup executes operations or write to its log. So basically you get the comments from the client, you put that in your log, you transmit your log to the backup, and backup have now the same log with the primary. You remember last time we were talking about the log has the truth of the system, right? And then that's what matters. So for this primary backup replication, we can have two different basically approach for replication. We can have asynchronous replication or synchronous replication. In asynchronous replications, primary gets operations, primary execute the operations. So these 4 are the same steps, like 1, 3, 5, 1, 3, 4, 5, the same thing we saw. So in a synchronous replication, primary get the operation, primary execute the operations, okay, and acknowledge the client. Primary orders operation into log, replicate, and send it to the backup, then backup write the logs. So this is asynchronous. And in the synchronous replications, primary get the operation, okay, order it, put it in a log, pass the log to the backup, okay. Then primary, I mean, just notice here, primary still didn't execute or didn't acknowledge the client of execution of the comments. So primary basically replicate the logs to the backup. Primary gets acknowledgement from backup, then acknowledge the client. Is that clear? So we can have two different ways, asynchronous or synchronous replications. And basically they can have, the benefits here is we make sure that before we acknowledge the client that the operation is done, the backup already have this operations. The issue can be, for example, if in this example, the issue can be, in this example, we acknowledge the user without the backup still having the operations, okay? Remember we were talking about all or nothing? So the issue here would be, what if I get the operation, I acknowledge to the, I execute the operation, I acknowledge the client, at the same time primary, basically backup will be dead. So what happens that that all or nothing consideration is failed here in this example. So we don't want that, okay? We don't want to have those type of basically scenarios. So we're going to with synchronous replication. We make sure that basically the operation is successfully arrived to the backup. We wait for the backup acknowledgement, then we acknowledge the client that the operation is done. So another point here is the primary doesn't need to wait to execute the program. It's just waiting for acknowledging the client. I mean, primary can get the operations, execute the operation, pass the operation to the backup, but not yet informing the client that the operation is done, because that can cause issues. So we're going to talk about that. So why does this work, this synchronous replications? So imagine we have basically clients with all clients with the operations. We have a primary, we have the backup, we have a login primary, login backup, and they are basically, same because they're supposed to be state. And we have basically a state machine and logging modules. So basically the client send the comment, let's say in this case, these are the command, add, jump, move, shift left to the basically primary. Primary put that operation in its log. As you remember, replicate the log to the backup. Okay, the backup puts the operation in its log. Then primary basically start operating that or changes state, informing the client, and then backup also does the same operations. So another thing, as mentioned, replicated log is replicated state machine because the log has the truth about the system, about the state of the system. And then, so using this, you can see it's work. All server executes same command and in the same order because we are replicating basically the log in the same log in both primary and the backup. Any questions so far about primary backup replication? It's very, I mean, nothing weird happening here. Everything like sounds logical and simple, right? So nothing weird really. So we don't need just to have one backup. We can have several backups. Okay, it doesn't change the fact at all. So still the workflow would be the same: getting operation, updating your log, replicating your log in the backup systems, then basically changing the state of the machine and basically acknowledging the user about the operation has been done. All clear? So we discussed
when you have more than one backup, do you need to tell what is the primary backup or how the operations are going to be done?
No, I'm going to discuss about that. What happens if you have multiple backups? So what happens if the primary fails? Which backup is going to take over? That's the question, right?
No, actually, no. You said that when you are doing the synchronous replication, one of the backups, well, in the case when you have one primary, one backup, the backup is doing the operation, then it's acknowledging the primary, then the primary is doing the operation, and then it's acknowledging the client. When you have more than one backup, all the time the same backup server is going to do the operation in this, and then it's going to acknowledge the other ones, or it can be a different one each time?
That's perfect question, Pedro. I'm going to discuss that. Basically, if I rephrase the question would be, okay, I update the backups. So should I wait as a primary? Should I wait to receive acknowledgement from all the backups till basically acknowledging the client about the operation has been successfully done, or should I wait for one reply, all reply? So yeah, there is basically a way I'm going to tell you. You don't need to wait for all of them to acknowledge you, okay? Because some of them can fail, some backups also can fail. Okay, you don't need necessarily waiting for all the backups, but I'm going to discuss that. Usually we have this, we say like if you have two F+1 machines, okay, like if you have, then you can basically handle like basically F failure in your system. So in this case, for example, if F is 1, it means we have 2 F+1 basically servers, okay? Then we can handle one failure. If one backup fails in this system, it's perfectly fine. Or if we have 5 systems, 2 of them fail, we have 3 still that can work. So basically, we wait for that. Basically, how to say, F+1 reply. I'm going to discuss that just today, but that's very valid questions. So we discussed that basically we want the operation. We said that's a key assumption. Like you remember in the primary backup example, we said the operations are deterministic, so there is no randomness involved. So for example, in that case, it means no events with ordering based on local clocks, because that can be some random, not totally random variable, but that's a variable not known to other replicas, right? Because we already discussed that the local clock can vary between so many different replicas. So we don't want any event with ordering based on the local clocks. So we convert timer network user into log event. We put all those basically variables into the log events in order to make it deterministic, even if the operations are not deterministic. If there has to be something, if the operation has to do something with local clock, we want that local clock also to be included in the log events, so the replicas can know about that. Because if we need the determinism, as I mentioned here, we need to make it so. But we don't want anything using a random input. If anything is required, we put all those in as a log event. And then the execution order of the operation would be identical. And another thing is a replicated machine is a single threaded, of course. Okay, we don't want if it's multi-threaded, there would be other issues. So remember that whatever so far we discussed, we want to talk about those using this case study, which is a design of practical system for fault-tolerant virtual machines, written by these guys. So they are from VMware, and the paper came on 2010. So we want to talk about this case study, how they achieve basically a fault-tolerant virtual machines. Anyone here work with vSphere from VMware as a hypervisor? So vSphere actually started in 2009. So basically what we are discussing is what they did like a year later. So the idea is basically how it was like an ambitious system from VMware, okay? So the idea was they want to give an entire virtual machines the benefits of primary backup applications. So the goal was replication of the whole virtual machines, and they wanted completely transparent to applications and clients, and they wanted to achieve high availability for any existing software. So basically what they were trying to do is running a virtual machine on top of primary backup application, whatever we discussed so far. So let's see what they did here. Nice recording. So, okay. So this is the basically overview of the system. Okay, so we have 2 or more virtual machines. Okay, let's say like 2, like in this particular example, 2 virtual machines, and we have a primary and backup, and they can be on different bare metals. And we have a logging channels which runs over the network, and we have a shared disk, which can be basically they will be connected to that via fiber channels. So this is basically a setup. It's important because the disk is not replicated. Okay, instead it's shared. So it's important for whatever we're going to discuss later to know the architecture, what they did. The disk is not replicated. Okay, they are using the same shared disk. All clear? So to replicate the virtual machines, they need to look at the virtual machine as a black box, which with like a certain inputs and certain outputs. So virtual machine inputs can be incoming network packets, disk reads, keywords and mouse events, clock timer, interrupt events. All those can be like a input variables to this black box, the virtual machine that we are seeing as a black box. And the output can be outgoing network packets and disk writes. So basically the input is everything that's flown into this black box or into the virtual machines, and the outputs is everything that flows out of this virtual machine or black box. But the question is why the disk write is as a virtual machine's output, not as inputs. It's a question from you.
Because of the logs?
Because of the what?
Because of the logs, you need to write the logs, whatever is happening inside the black inside the VM.
True. Yes. No, not precisely. If you remember, we discussed this disk is shared. Okay. So basically, the write operations are going out of the virtual machines. So basically, these writes are considered as output because they go to the shared disk that is attached to the both virtual machines. That's why I said the disk is not replicated, the disk is shared. So the write operations are basically output events that we are writing in a shared disk between 2 virtual machines. So let me see if I can find something here. So if I go to the, let's see what I can see. I'm just checking this. So this is basically VMware vSphere, that's what we were discussing. Let me see. What does this mean as? Do you hear the voice?
Yeah.
Yeah. I thought there would be some architecture showing there, but no. Okay, so this is basically what we were discussing, how sort of they achieved that in those earlier versions. So these writes are output operations because they are writing on a shared disk. It's a very cool thing actually to check it out later by yourself. For example, you can use this vSphere as a hypervisor. It's like a sort of virtual machine sitting on your own personal computer even, and can give you really good deal of security if you're doing something related. I mean, something very sensitive, you want to have a really nice secure system. That's a really nice way to go. Sorry. So, okay, so this was the architecture of the whatever we discussed. So these are the challenges, okay? So the challenge is making the backup an exact replica of the primary. Here by exact replica, okay, I want to highlight, that's why I put exact replica, is we want to somehow deal with the non-deterministic operations as well. We don't want just deterministic operation. We want to make sure we can deal with non-deterministic operation as well. So that's one of the challenges that they were trying to solve, okay? Another one was making the system behave like a single server and avoiding two primaries or split brain. Because remember, we are talking about primary backup operations, so we don't want the network to be broken into parts, and then we can somehow these two replicas can think they are both primaries. That's what means like a split brain. So before we continue, let's have like 7 minutes break. Okay, we come back 7:40. Okay.
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 So what we were discussing about this basically project of the VMware, trying to basically have a virtual basically machine on top of primary backup applications. And what we discussed is these were the challenges that they're basically the paper, particularly the papers, okay, trying to address these challenges. So basically the idea here is, like, as I mentioned, if you want to model virtual machines as a deterministic state machines. So to do that, we have to convert a non-deterministic basically operations to deterministic operations so that the state machines replication can basically be the same at two different stages. So what we said, as I mentioned, that we log results of all the input events, okay? So basically, including current program control value for each, because we want somehow to record all those causes of indeterministics into the log events. And the inputs can be basically the packets with any data that can basically arrive, basically keystrokes and all those events can be converted into the event and like stored in a log. And log results of non-deterministic instruction, as I mentioned, we want to have those. So we log results of timestamps, counter rates, and those things. So once basically the primary has logged both causes of non-deterministics, the backup can use this information to update its state, and basically both primary and backup can end up in the same state. In the step 2, primary hypervisor sends log entries to backup hypervisor after having those logs sent to the backup hypervisor. And backup hypervisor replace the log entries. So you have the log entries in the primary, send it to the basically the backup, and the backup starts replaying all log entries. And we stops backup the virtual machine at the next input events or non-deterministic instructions. In this case, we deliver the same input as primary so far, okay, and delivers the same non-deterministic instruction result as the primary did. Is that clear? So basically, in this case, the backup would be always one step behind the primary, okay? But we're going to discuss that. So that's how we can achieve basically exact replica of the primary can be happen in the backup as well. So now let's talk about making the system behave like a single server, or how we can deal with the fault in the system, or what is the fault tolerance protocol. So when backups take over, non-deterministics makes it execute differently than primary would have, okay? And that is fine. As I mentioned, for example, there are certain events that can happen in the primary, like as I mentioned, local clock, for example, just one example. Those can, when it goes to the basically the primary in the backup, it may cause the backup to execute differently, and that's fine for this stage. And when backups take over, execution is consistent with output the primary has already sent. Let's basically see that how inconsistency can happen using like this example. So suppose in this example, we have basically primary, okay, and backup, as I mentioned, and primary is accepting the inputs. So primary just fails just after an output events, okay? And like let's say like an in-flight events that backup doesn't know whether the events came after or before the output events, because the primary fails at this point. So this really red events that I put here may have influenced basically value of output backup. Okay, so basically the backup doesn't know what happens there. Basically, there would be some confusion there. And primary also doesn't know what the value of the output event was, because it just crashed right at that point, okay? So primary also cannot fix this. So this can cause like certain inconsistency, okay, in this example. So let's see how basically this vSphere or this project of VMware dealing with this type of situation. Basically, that's what I call it, like the fault tolerant protocol, what they call it fault tolerant protocols. So primary logs each output operations. So you get the input. The inputs are coming, as you remember, and the outputs operation also are logged. But as I mentioned, like in the previous example, primary delays the output. Okay, delay sending output to the basically to the user until backup acknowledge it. So the primary waits for the backup acknowledgement about all the events, okay, and the output before it basically inform the client. As I mentioned, but same thing that we discussed last time, but does not need to delay execution. So we can basically the primary can get input, okay, logs all this in the backup, and also log the output, wait for the acknowledgement from the backup before informing the basically the client about the operation has been done. But the execution can take place. We don't need to wait for the execution. That doesn't cause any problem. So, and this, there might be some example in just using this that output, we show basically 2 times output to the client, okay, and that's fine. So it can be, that also can be caused due to, for example, duplicate network packet or duplicate write to a disk. So that doesn't make the state of primary and backup different. So there might be, like as I mentioned, there can be duplicate events, duplicate network, not duplicate network packet, duplicate, how to say, duplicate output that we can show to the client. So in this example, we can restart execution at an output events, by the backup, because the backup also have the output, and the output was not acknowledged to the user before the acknowledgement. So if there would any crash here, there wouldn't be any issue. So there is this metaphor I heard in Mexican, they say, ojos que no ven, corazón que no siente. Okay. So what the idea is basically, it's not a good metaphor, this one. Okay, so let's come up with a better one.
I think it's a good one.
It's a good one? Okay.
Yeah,
I mean,
if the client doesn't know, no problem, right?
Exactly.
And we
So
totally
it makes sense. Okay.
Yeah.
I thought
Exactly.
I heard this in another context, so I didn't know it can be applied to this context as well. But what the other basically metaphor that we can say is, if a tree falls in the forest, okay, so basically who get notice about that? There wouldn't be any issue, right? So that's the same thing that's happening here. What's happening here? If the client doesn't notice it, so who cares?
Yeah, I just have one question there.
Mhm.
How the backup knows that the primary has failed?
I'm going to talk about that. Basically, they send heartbeat packets to each other. They keep basically pinging each other constantly, primary and backup, in order to know that they are both working. So if the backup doesn't hear from the primary, then of course it means primary failed, so backup need to take over.
But how the backup knows what is pending for doing?
So that's the idea. There is nothing pending, because basically the backup can restart execution at an output event, because that's the last thing. Basically, in this example, I'm talking about this example. In this example, that's the last thing the backup got from the primary. So the whole idea here, what we're talking about, exactly that situation that you're saying. What happens if one of them fails? Mainly, let's say primary fails, which can be basically more problematic. So primary is constantly getting input from the clients. Like the operations are coming constantly, not even one client, can be multiple clients. And all those basically inputs are logged and passed to the backup. But basically the client or the user doesn't know what's happening there, right, behind the scene. So the backup always has this latest state. So as anytime the primary fails, the backup can take over without any problem. Even, for example, in this case, the primary get the, let's say, input, let's say, execute the input, okay, and then acknowledge the basically backup and then fail. So there is no issue there, because backup can come to the basically become the primary and inform the client about that basically the operation is executed. And even in this case, client would just hear one time confirmation of the operation, execution of the operations, because the backup, that's the idea. So when the primary basically doesn't acknowledge the users, okay, so till then we can have operations in the backup. I don't know, am I saying it clear or not? Or did I just make it more confusing?
No, it is clear. The only thing is that you said the primary fails before executing, I think, or after executing the operation in this case.
In this example, we have the basically, in this example, you can execute, okay, but if you don't receive basically, like, let's say you get the input, you execute, and you basically you get the input, you send the basically updated log to the backup, and you're executing and you finish the execution, still you haven't heard from the acknowledgement from backup. And while you're waiting for the acknowledgement, you fail. Okay, so that operation can be basically executed in the backup and comes, and then basically output can be sent to the user or the client.
Okay.
And the last challenge that we discussed is like avoiding two primaries or a split brain. because what can happen in that example, if you remember, we have virtual machines logging channels that happens over the, let me go back so you can remember the architecture. So this was the thing. Okay, so what if the issue is, what if this logging channel fails? If this logging channel fails, this primary and backup basically are disconnected, and they both might think, okay, I'm the primary, okay, I lost the backup, and the backup may think, oh, primary is dead, so I'm the primary one now. So that can be, basically, that's what we call that, like a split brain, which is another issue they're trying to, we need to basically try to deal with. So the idea is primary and backup, which runs that's UDP heartbeats to monitor logging traffic from their peers, as you mentioned, how they get to know that some of them fail, one failed. And idea, another thing is, before going live for the backup or finding a new backup for primary, because if basically if the primary fails, the backup needs to go alive, become the primary, and if the backup fails, primary needs to find another backup. As I mentioned, it's not necessary we can have one backup, we can have several backups in a like idle state. So before they do that, they execute an atomic test and set on a variable in a shared storage. And if the replica finds variable already set, it abrupts. Okay, it means basically it's kind of, anyone, okay, before going there, anyone knows this test and set? Anyone heard about it?
Not from my side.
No.
Who knows about it? Jordan, you know? Ah, okay, Jose, can you tell us what is it?
Yeah, it's, well, an operation from the CPU that it's done on one cycle. I mean, like it says it's atomic. It first check the value that is like the test, that it's like the previous value that you had. And then it does the set on the same like instruction. No one else can do it because it's atomic. And then it checks that like it's set right. If you do that, then you are guaranteed that the value that you're setting there, it's the one that CPU is setting, and no other value from all the other CPUs.
Okay, so you deal with that in a programming or doing something else?
Like programming?
Programming, okay.
Right. Yeah.
Yeah, it's basically, as you said, that can be, I mean, as Jose said correctly, that can be one usage, okay? Or mainly, I mean, as you said, it's atomic, it's basically, it's linear operations, okay? And it's basically it's used for locking and operations, okay? So how it used, I mean, you can look at it for, like, I think there would be a very long Wikipedia page for test and set how it works. The whole idea here is they want to make sure that the whole idea here is this primary and backup. They want to make sure that one of them really failed, not that the communication channel between them failed. That's why they can basically go and write a variable on a disk which is shared between both of them. Okay, so let's say the communication between these two are basically failed, but they can go and check this basically. The varies can set a variable basically in the disk, and they can go and both check that variable and see if this variable has been modified by either primary or backup before that. So if that's happened, it means basically they are both alive. Okay, or if primary checks and see the variables change, can know the primary is alive, and basically the communication channel between them failed. Or same thing, if the backup see the variable change, can this detect the communication channel between the failed, primary is still active. So basically, it's kind of like a lock operation, work for so many different reasons, but mainly for locking certain resources or operations. So So what we discussed with this basically virtual machine fault tolerance is a challenging application of primary backup replications. It's designed for correctness and consistency of replicated virtual machines outputted despite failure. And the performance result that they show in the paper, okay, show that they achieve high performance, low logging bandwidth overhead. So it's basically a nice project done by the VMware. And I believe that that was the starting of that sphere technology that they are now proposing. Of course, not exactly the same, but the earlier version was having the same idea. So in summary of primary backup replications, it's a first step in our goal of making stateful replicas fault tolerant. It's not everything, but it's the first step, okay? And it allows replicas to provide continuous service despite persistent net and machine failure. And it finds repeated application in practical systems, which we're going to discuss next. So far, remember what we discussed is, yeah, we have a long way to go. What we discussed is primary backup replications, okay? So we're going to discuss more, basically, more about this. So this was the same thing that we discussed from the first slide. So we nominate one replica primary, just to give you a quick review. Client send all the requests to the primary orders client request. Okay, so that's what we discussed. And we said that we can go from 2 to many. Okay, it's not necessary we can have 2 backup. In that some case, maybe some backup can be even idle. Okay, not necessarily all of them can be active. We can have primary backups, active backups, idle backups. So now we wanted to basically earlier what we discussed is primary backup. Okay, and we mentioned about that case study with the VMware. Now we want to talk about state machine replication with many replicas, okay, which can survive more failure, not just the primary failure or the backup failure. So we want to talk about surviving more number of failures, as Pedro was asking. So we want to talk about use stamp replication, or the paper that I mentioned at the beginning of the class. So we want to have this state machine replication for any number of replicas, not limiting ourselves to 2 or certain numbers. So we have a replica groups of 2 f+1 replicas. So f can be any number depending on the application. And in this replica group, 2 f+1 replicas, we can tolerate f replicas crashes. So if we set like 5 replicas, okay, then we can tolerate 2 machines failing. So basically it means like we have the majority of the replicas working, minorities are failing. If we have 5, we can tolerate 2 failure. If you have 7, we can tolerate 3 failure, and so on. So there are certain assumptions for use stamp replications. The first thing is it handles crashes failure only, okay? Replicas failing only by completely stopping. So here we are not talking about replicas behaving weirdly, okay? That's totally out of context here, okay? If the replica is alive but not behaving normally, that's out of context. So if we are talking about failure, we are talking about like a complete crash, total failure. And also the basically unreliable network can be considered. So messages might be lost, duplicated, delayed, or delivered out of the order. So all those basically the requirement that we were avoiding to address from early classes. So we have the identities of basically the system has the identities of 2 f+1 replicas. And we have in-memory log with clients requests in assigned order, the same thing that about the primary backup. So the normal operation for this, and now we are talking about more backup, okay? So we have a client, we have a primary, and we have, let's say in this example, f is 1. So we have 2 f+1, we have 3 systems, 3 replicas, one of them working as primaries. So normal operation can be like client requesting, okay? Primary adds request to end of its log, same thing that we discussed. Then primary send basically this prepare packets to the backups, okay? And replicas add requests to their logs in primary's log order. Then replicas inform basically or acknowledge the primary that they, let's say, prepare OK package, like they prepared, they got the log and their log is updated. And in this example, what Pedro was saying is like example, primary waits for F prepare OK. Okay, it means to inform the client that the request is committed. So in this example, like this very simple, simplified version, like you have 3 replicas. So clients can, the primary just need one basically prepare OK package or one confirmation to inform the client that the operation is committed. And by setting that one, it means no matter, even if the primary fails, it makes sure that there is another replica having the updated states, at least, right? So in this case, three replicas, primary waits for one, at least one, basically prepare OK or acknowledgement before executing and updating the client. Again, I highlight here because primary want to make sure at least another replica has the updated log, at least, because primary can fail also at any time. So at least another replica has the latest, basically, the state. So these protocols basically provide state machine replications and execute primary nodes request in F+1 or 2 nodes log. Even if F equal to 1, like as we've been discussing here, and we have crashes, okay, then still one, at least one basically replica retains request in the log, whatever I was discussing. So also we basically piggyback the commits. Okay, I'm hearing so far whatever we discussed is like about updating your log. We didn't talk about the commits, but let's say the packet comes from, or the request comes from the clients. Primary updating basically send this prepare message to the backups, and using this packet also primary can tell the backups to commit the previous logs. Okay, previous operations. Because whatever we were discussing here, we're saying, okay, you update the log, you say, okay, the log is updated, the primary execute here, another packet comes, primary say, okay, update the log and commit the previous operations, because the primary already committed the previous operations. Basically, the backups commit the previous operations, send the prepare OK or acknowledge for the primary with the new request. The primary execute that. So another case can be no client request after, what if there is no client request after a certain time? What happens for the primaries? Primaries send commit message to all the backups. So if, let's say, there is no, basically there is no new request from the clients, after a certain timeout, primary informs the backup that commits all the previous, basically, operations. So far, go ahead.
I have a question.
Mm-hmm.
I don't know if it is in the scope of this topic or in what you're talking, but in this case, when a replica dies, it's not alive for a short period of time, it will miss a lot of events in its log. What will happen when it comes back to the life? How that replica achieves or it's synchronized with all replicas?
That's actually perfect.
The shared disk, right?
Pardon?
It's because we have a shared disk.
No, the shared disk was just an example of the vSphere with the virtual machines.
Oh, okay.
Not, I mean, that was just a case study to see how virtual VMware used primary backup schemes in their own basically vSphere in order to basically come up with a scalable, available virtual machines using the primary backup operation. But what Saul is saying, what if a backup fails, if a system, whatever, one of the replica fails, go out of the operations and come back after certain times. So we have all these logs, right? Log operations. And basically, the log need to be replicated again, okay? Or the primary, the backup should get the latest, let's say, the best way is like looking at the latest snapshot in the systems, okay? And basically updating its state with the latest snapshot. Again, it depends on, like, for example, you're talking about like, okay, the backup fails, okay, then come back alive. Then like how long was that disconnection, right?
Yeah.
That can be like, if there's like a day or like week, then there can be a lot of operations, like everything changed basically. A lot of things changed. So usually the issue, those issues, like I don't consider that failing. If there is something like that, totally complete replica comes and there are a lot of basically events, those are basically replicas that completely fail and they're going out of operations, and maybe a totally new replica is added to the operations. In that case, basically their disk need to be basically updated completely. It's not about matter of few operations, missing operations in the log to get updated. It's about totally new state because of the time that you're considering.
Okay. Okay.
I hope I answer your question.
Yeah. Thank you.
I have another question, Mari.
Go ahead.
I mean, in this case, we're talking about ideally, right? But for example, in the real life, sometimes you don't have the same resources for having a backup or having a primary. So sometimes you decide that the primary is going to have the better hardware, and the backup is going to have maybe better in another resources, but for some reason you have the primary. So when the primary is going down, the backup is going to be now the primary. So what happened if suddenly you need to restore your old primary? It's going to be now a backup, right?
Mm-hmm.
Yeah, but what about if you want that one to be the primary always that it's available?
You mean what if the primary goes out of operation, you want when it comes back to the operation to be the primary?
Yeah.
Again, okay, many things here. First, that can be basically simple setup. When this system is available, this is the primary, so the client always talks to the system. There is no complication there. But whatever we are discussing now, from like 2 weeks from to now and in the future, is we are not anymore talking about a horizontal scaling. No, we are not talking about like vertical scaling.
Vertical,
I'm sorry. We're not talking about vertical scaling or adding more resources. So we are talking about horizontal scaling, having basically, and we're not talking about here, mostly we are referring to really like data centers, right? Servers and data centers. Like two different servers, or let's say servers in a different data centers. So, but if that's the case, if they are not like homogeneous servers, if there are one server much stronger than other servers, you can always set that as a primary. If it's available, it becomes primary. That wouldn't be any issue with that. It's a matter of like how you set up your system, right?
Okay.
So whatever so far we discussed, it works for F failure. If F failed backup replicas, right? We were discussing here, we say, okay, we have primary, client, primary, backup. What if C fails, or what if B fails? So what we want to discuss now is what if the primary fails itself, okay? So in this case, if we don't consider that situation as we were asking, if the primary fails, it can basically, the system can halt despite merely a failure. For example, we have five replicas and the primary fails. So we need to talk about this situation. What happens between that remaining replicas that are operating? So for that reason, we can use two different approaches: view stem replication and view servers, and we're going to discuss that. So let's define what is the view. I mean, I'm talking about view server or view stem replication. A view can be basically, we can set let different replicas assume role of primary over time. Okay. So, and the system can move through a sequence of views. So each view can be basically in view number 1, this system can be primary, and this is backup, and this is backup. View number 2, this is the primary, these are the backups. In view 3, this is the primary, and the others are backup. So we letting different basically replicas take the primary role, and we call each of them a view. Is that clear? And then we're going to talk about view change protocol. So we're so clear now, right? So if for example, we are in view 1 and this primary fails, okay, so what we can do is simply to switch to another view, right? That the other replicas is the primary, not the previous one. And as I mentioned, backups, replicas monitoring the primary, there's always this basically heartbeat UDP packets between them. They are pinging each other constantly to make sure they are operating. But if a primary seems faulty, okay, for example, you wait for a long time without receiving any prepare or commit packets, okay, it means the primary has some issues. So the backup can execute the view change protocol to select new primary. And what it is, view change protocol is basically changing the view or going to another view, which is another replica is a primary one. And again, to remind you, we need to keep clients and replicas in sync. So same local state of the current view in all the replicas. So that's the thing, okay? And same current view at the client side as well. Clients should stay in synchronization with what's happening. So in order to correctly changing the view, going from this view with this, let's say A as a primary to another view, which is B as a primary. So view change happens locally at each replicas. Okay, there is each replica basically does that locally. So all primaries execute request in old view and new primaries execute request in the new view. So that can be the case. For example, for sometimes you didn't hear anything from the primary, okay? So you consider primary fail, you do the basically the replicas start doing this view change protocol and they shift to another view, but primary is still maybe working in old view and operating executing the operations. But what we want to make sure is to make sure that the state machines basically are replicated correctly and they are in the same states, all of them. Let me talk about this with the example. So in order to do replica states, okay, you sort identities of all these true F+1 replicas that we have, okay. We already discussed about in-memory log. And we have this view numbers, okay, which identifies primary in configuration list. So for example, you have view 1, view 2, view 3, and each number of those numbers is 1. For example, view 1 basically because we are sorting basically all these replicas. In view 1, the first one is the primary, view 2, second one, and so on and so forth. And the system basically state can be in a normal or in a view change state, because if everything is working, or system is started this view change and trying to change to new primary. So imagine this case. Okay, we had A, B, and C. Now A is failed for any reason. We didn't hear, let's say, any update from A, and there was no, basically, it was not answering the pings. So B, in this case, start view change protocol. B notices the A fails, send start view change to the other replicas. C replies, do view change to new primaries with its log. And B waits for F replies, then send start B. Okay, in this example, F is 1. If you remember, we had 2F plus 1. It means we had 3 replica, one of them failed. So in this case, B waits for one more replica to replies, okay, before it's switching to the new view. And on receipt of the start view from the C replace the logs, okay, and start the new operations. So, sorry. So A was the old primary, now B is the new primary. And remember we were saying, let's say all primary, which is A, is executed these operations, right? What I wanted to discuss here. Okay. All primary A must have received 1 or 2 prepare OK replies for that request. Remember what I was saying here? That the basically all primary is executing the operations in the old view, okay, and the new primaries, which is B, executing operation in the new view. So why this cannot cause us any issues? Okay, that's the question. You remember that in this type of case, it doesn't cause any issues because we said that in order to primary to execute an operations, you need to wait for F plus 1 from F replies, right? That was the conditions for the primary in order to execute. And we said in this case that we had 3 replicas. Primary needs to wait for at least 1 prepare OK or acknowledgement in order to execute operations. So when we change the view to new view, at least one of these other replicas has the has the latest state. Is that clear? I think I'm making you lost. So the idea here is what I'm trying to say. When we switch the views, definitely by the condition that we said, one of the other replicas have the latest states, at least. So everything, all the operations will survive to the new view. There wouldn't be any operation that missing, because if A fails and A execute this and failed them, we know that basically one of these B or C at least has this operations, because A couldn't execute this without receiving 1 acknowledgement at least. So the whole principle, the thing that I'm talking is called quorum. Quorum. It means any group of F plus 1 replicas is called quorum. And quorum intersection property means 2 quorum in 2F plus 1 replicas must intersect in at least 1 replica. So if you have 3 different replicas, okay, and any quorum is a F plus 1 replicas, means if you consider F1, any quorum is 2 members. And there is this intersection property, means that if you have these three basic replicas, and you have a quorum there, and you have two quorum there, it means there should be at least one overlapping replicas. I mean, it's don't get confused again by the names, and there's nothing confusing here really. I mean, the whole idea is one of this replica at least has the latest operations. Even if the primary fails, there is one of them at least has the latest operation, and that latest log can transfer to the new view. So there wouldn't be anything missing there. So it's the same thing here. I'm discussing in the normal operations, okay? And if we have basically Q1 and Q2, Q1, Q2, basically the overlapping part between Q1 and Q2 at least has one replica that has the basically latest operations. Even in the view change stage, the overlapping between two different quorum has at least one replica that contains the latest committed request. So in a normal basically operations, okay, the operations moves basically have two different quorums have the overlapping replicas that basically you're replicating your state machine correctly. Even in the view change, when you change the view on primary fails, you pick another new primary and you do the view change, there would be at least one replica overlapping that contains the committed request. So there wouldn't be anything missing, okay, in that case. So talking about this split brain issues that we discussed before, we define what is it? It means two different basically. We have in this basically system, we have two different primaries, okay, at least two different primaries. So we have this situation, client one talking to primaries, and there are other basically replicas, and we have not just one client, we can have multiple clients, right? So there are basically requests coming, executing, requests coming, executing, okay? And at a certain point, the network is partitioned. So this primary and these two replicas, or this replica A gets disconnected with other replicas, network is partitioned, primary didn't fail, but the network is partitions. So this primary B, let's say, start view change protocol, okay, and start the new view, and then after they start the new view, they can start getting the requests from other clients and start executing them. It's correct? So the question for you is, what is undesirable about this sequence of events? I mean, there was a question and I answered before from one of you. So what is the undesirable about this situation?
That maybe you can lose information.
That
maybe the system can lose information. Because you're... No, go ahead.
No, okay. Can you elaborate it? How the system can lose information? It's correct, but I want you to elaborate it. Discuss it more detail, how it can happen.
Yeah, because the system is saving information in different partitions, and maybe when it's tried to avoid their replicas, maybe the system lost some message or something like that.
Yeah, you're right, as you're saying. I mean, we have a network partition. We have basically certain operations happening in this part of the network, another type of operation happening here. Okay, so there is two different states now. Our system, our distributed system have different states now. Their state doesn't match anymore, and I mean, you cannot do anything about this. So this is very undesirable situation, right? And why won't this ever happens? And what happens instead? So two more questions. Why we never going to face this type of issues?
because probably if this happens, I don't know, the original primary will never get the F responses, and it will execute the client request.
Exactly as you mentioned. I mean, this is not going to be the case because primary, to execute these operations, primary needs at least F prepare OK, right? F confirmation message. And if the primary doesn't basically get that, it's not going to do the operations. So this basically doesn't happen. So what happens instead?
The full system will hang, right?
The whole system will hang?
Or probably I didn't.
No, but you mean in this situation, just talking about these three replicas, this scenario of three replicas? So we said, okay, this is undesirable. We know why, because they end up in two different states. But we said this never happens because primary is not going to execute any operations because that primary cannot receive F other confirmations or another one confirmation. So what happens instead is basically this part of the network doesn't work anymore, right? So this is basically a part of the network that is operating now.
Okay.
So now this B as a new primary has the latest state, and this is the correct state of our distributed system, which B has it as a new primary, because everything is working still. B has one replica and one backup, and start getting basically getting the execution running and say without any problem.
So what is going to happen with the request from the client one?
Basically, this let's say network partition. If the network at some time get connected again, the primary comes back to the operations. Okay. Now, as a primary, okay, I'm going to discuss that. But primary comes back to the operation, and primary would detect that the view change. Now, primary is a backup in the new view. Basically, primary can join this new view as a new backup, because in the current view, B is the primary.
But the variable is set for what, right?
Which variable?
Yeah, the variable that is going to set who is primary now is set for both in different in the both cases.
Yeah, you remember we were discussing that clients and backups and basically clients and replicas are stating in the synchronization. I'm going to talk about that particular case, how a client can know the view changed, right?
Okay.
And
yep.
how the primaries can know the view change.
Yeah, but in the case that we were analyzing, the client is going to wait forever, or are we going to have some kind of timeout there? The client one.
For the client one, I'm sorry, I thought we were talking about the primary. For the client one, basically, okay. I mean, if the client one cannot basically somehow for any possible reason communicate with this, clients one needs to wait basically.
Yeah, but in this case, client one has sent a request to primary A in this case, and is not getting an acknowledge even when it has been executed. So the client is going to wait forever, or we are going to implement some kind of timeout, or.
So the idea is when basically, in this case, when we have a switch to new view, all the clients now start talking with the new primary. But it can be a case that, like, let's say weird case that network totally partition, okay, and client one, for any possible reason, cannot reach any other replicas. Because we are talking about all the clients are always talking with their primaries, all the clients. But in this case, okay, if, I mean, this was like a hypothetical situation that I wanted to show this cannot happen. But even if that's the case, then client won't really get disconnected with other, I don't know, other part of the network for any reason. Like let's say this continent totally gets disconnected from the other continent, then of course there can't be done anything for this particular client. But the way that I put it here is I wanted to show it never happens, because all the clients always talk with the main primary, all the clients.
Okay.
It's not the case like this client talk with this client talk with another replica. All the clients always talking with the main replica. So as mentioned, for view changing, we have another basically approach using the view server. So view server, the idea with the view server is we can basically centralize this changing the view, not letting all the replicas decide by themselves. If you remember in the previous one, we said the replicas deciding locally. But what if we can have a basically centralized all the operations, having a centralized system that can say, okay, now you are the primary, now you are the primary, now you are the primary, and controlling or orchestrating these changes between different replicas. So it's the same. The goal is still only one primary at a time for correct state machine replications. That's always what we are looking for, but now using a centralized approach. So for now, you assume view server never fails. Okay, the server that controlling who is primary never fails. We're going to discuss about that when we are talking about the consensus protocol, how they coming to the agreement, all the basically replicas about certain values. But for now, let's say view server never fails. So each replica periodically pings the view server, and view server declares replica dead if it missed and pings in a row, and view server consider replica alive for a single ping received. So view servers constantly getting to know all the replicas, if they are alive, if they are dead. That's it. So the problem can be here is replica can be alive, but because of the network connectivity, we declare dead. So let me again simplify here. Say this example. So we say this is the view server, okay, orchestrating who is primary, who is the replicas, who is the basically who is the backup, primary, who is the backup. And as I mentioned, you can have more than backup. Let's say other backups can be idle backups. We have client, we have view server, we have all the replicas. So as I mentioned, the view server decides the current view, and we have a view number, who is the primary servers, who is the backup servers. Like this example, we are in the view number 1. S1 is the primary, S2 is the backup. Let's say. So if basically a primary dies, doesn't reply to pings packets, the view server switch to the new view. Okay, now we have we are in a new view 2. S2 is the primary, and S3 is the backup now. Okay, that's clear. So the challenge is here is all parties make their own local decision of the current view number. Okay, what view number they are. Let's discuss that about, especially when the network when the replica doesn't fail, but the replica cannot just respond from the view server, but the replica is still alive. So in general, any number of servers can ping view server. It is okay. I mean, these are basically talking about the current view. It's okay to have a view with a primary and no backup. That's perfectly fine. And we want everyone to agree on the view number. Okay, these are basically what we want to achieve. We want to make sure that all the replicas are agreeing on what view number they are at the moment. So what we can do, we can include the view number in that RPC packets between all the parties. in order to make sure all the all the replicas are aware about the latest view. If you bear with me, I'm going to finish soon. Okay, so you don't need to have a break. Okay. Oh, let me have a break here. No, but don't go. It's about break about topic, not break about the class. I want to discuss something. Let's just wait here. Let me get a break from the topic talking about this. I'm going to. You remember this Excel file that you can track your.
Yep.
Yeah.
Yep.
You can track your grade. Okay. I'm going to make another basically sheet there, and with your name, so you can include your title, paper title, okay, when you choose. So if you if you choose your paper and you came here and you see another students already have that paper, don't choose it. Okay.
So that will lose anonymity. I don't know how to pronounce that.
Oh yeah, that's okay. I put it with the student number. Okay. I mean, yeah. I didn't. That was a very good thought. I didn't see that really. That was very smart, right? You lose the anonymity, but the idea is I don't want two people pick the same paper.
I have another idea. Maybe the first person that choose a paper can enter the name, and then so on and so on. Everyone can enter their name and trying to have different papers.
You mean I don't put anything? I just say
just the paper title. Yeah.
Just put the paper title.
Yeah, I was thinking the same, because also with the IDs, sometimes you can know whose paper is that. Either way.
You can know. Yeah.
Yeah.
I agree.
Yeah.
Okay, perfect. Thank you guys for
Okay.
that help. I mean, I couldn't really think. I need more time to process all this information. So paper titles, we're going to have 23 paper titles. Okay, I'm going to remove this. So there is not an order. Okay, remember that. So come put your paper titles that you're picking. So if you see there is someone else already picked that paper, please shift. And I try to keep an eye on this. Okay, if I see there is a paper that is not really related or doesn't really fit what I'm looking for, I would quickly inform you. Okay.
Will you share the link of that Google Doc? Or
you have it already, no?
Yeah.
Because okay. We have a history for the editing.
Yeah, I was going to say also about the history. That
yeah,
well, not all, because a lot of times it's anonymous, right? If you make it public.
In the history,
it should be anonymous, I believe.
But yeah, that doesn't really matter.
Yeah.
I don't care.
But I think I believe when you're looking at the paper, I cannot even see who is looking at it. So I believe when you start writing it, it would be anonymous. But if it was not, then there's no other way. Okay. And it's fine. Whatever. I mean, don't be anonymous. Okay. It's fine. Okay. Anyway, the grading going to change, so it's not going to be matter really. If they know who is the reports coming from. Okay. Yeah, but a lot of issues really. I couldn't think. But yeah, just put the paper here. Let's say by end of this week, okay. But you have Thursday and Friday. Please put the paper here so I can check it, okay, and I can make sure. Let me change these things because change editor viewer. I stop making you be able to edit it because I need to check it later. Just give you edit to this document, not to everything. Okay.
Okay.
So by this Friday, please put the paper here, and I would check the paper, all the papers by the weekend. Okay. And if there was anything that I would say, okay, John, don't pick this paper, I would inform you by the weekend, okay, by Saturday or Sunday. So then you have all the next week to read the papers and come up with the summary.
Just the paper title, or also the link to the paper title?
The title is fine. I can find it. There's no issue. Just the title would work perfectly.
Okay.
Because the titles are unique, I mean, for sure. Okay. So okay, this is about this. So I fixed this shit from tomorrow. You can edit. We can put the title. So let me finish this quickly, and so we can rest. I mean, so there is no break, so you can just go and rest completely tonight. So that's the thing we're looking for. We want to agree and we want all the basically replicas to know the view number. And we want to make sure the primary has the up-to-date states. So in order to do that, only we promote the previous backups. We don't go and promote idle backup, because the previous backup is the backup that has the latest state, right? Or up-to-date state. So when a primary fails, in the new view, we promote the previous backup as the new primary, like as simple as that. And how does view server knows whether backup is up to date? View server sends view change message to all, and primary must acknowledge a new view once backup is up to date. Again, like some very okay. Let's talk about all these things with example here. So let's say what issues can arise. Okay, let's putting all those things that we discussed together and see what can be the issue. So we have view server. This is working perfectly fine. We have a client. As we mentioned, client is in synchrony with all the replicas. So the current view is view 1, S1 is the primary, S2 is the backup. So what happens if the S1 get disconnected from the view server? S1 is not failed. S1 just get disconnected from view server. View servers cannot ping S1 anymore. View servers switch to the second view. S2 is the primary now. You remember we said it's fine to have just primary. You don't need necessarily to have a backup. So S2 is now, this is the state, right? S2 is we are in the view 2. S2 is the primary, and there is no backup. And S1 is still think S1 is the primary, and we are in the view 1. So, so one possibility can be before S2 here from the view server. Okay, view server switch the view. S2 is still in the old view. Okay. So in this case, basically clients communicate. Okay, send the packets to this one update this 2. And then at this stage, client get to know about the switch of the view. Client get to know that, okay, view server is telling me I have to switch to the second view and communicate with S2 as the primary, but S2 is still in the old view because this packet doesn't arrive here for any possible reason yet. So S2 is not aware of this. So in this case, when a client informed in basically trying to communicate with S2 with certain operations, S2 cannot, of course, run these operations because S2 thinks S1 is the primary. So this packet would force basically S2 to fetch a new update from the view server. So S2 updates, it's basically, let's say, pings the view server about the latest update, the latest view, get to know that the view change, and then client can communicate with S2. So what if S1 is in the old view, client is in the old view, S2 is in the new view, okay? What would be the situation here? So client keep basically communicating with S1 because S1 is in the old view, S1 is the primary. So S1 tries to update S2, but cannot because S2 can rejecting this update because S2 thinks it's the primary one at the moment. So this basically operation cannot work. Okay, so S1 basically informs basically S1 would force client to fetch a new update from the view server, even if it cannot achieve the view or basically contact the view server. The client would contact the view server because the operation doesn't go through, and then client updates the view server to the latest one and then communicating with the right primary, because this is the right primary. Okay, it doesn't matter what they think, this is the right primary. Is it clear? So talking about the split brain and view change, the takeaway point is like the split brain problem can be avoided both in decentralized design using view stamp replication, in which each replica decide the view themselves and then communicating with other replica to decide on the who is the primary now. It can be avoided in the centralized control using the view server as well. And both protocol must be designed carefully so that replica state does not diverge. That's the whole idea about most of the thing we're discussing today is we don't want that replicas state to diverge. We want them to be exactly the same. So talk about the reconfiguration and the need for reconfiguration. What if we want to replace a faulty replica with a different machines completely? Okay. So we want to move one of the replicas for a permanent failure and add another one. So let's say it can be for so many reasons, decommissioning of an old replica or adding another replica to increase your F, because you're having 5 replica, you want to go to 7 replica now. So the protocol that handles these possibilities is called reconfiguration protocol, because what you're doing basically, you're reconfiguring your whole systems. You're coming with different number of replicas, or you're completely changing one replica. So replicated state for reconfiguration is exactly the same process that we discussed before, but with this new approach. Let's say using epoch number, which is basically indexes the configuration that we are currently in. So imagine this is the situation. Okay, we have client, we have primary, and other replicas. So you want to remove this C and you want to add new replica. So basically the process is the reconfiguration commands come, okay, from client. Primary immediately stop accepting the request from other, let's say, even if there's other clients that communicating with it. So clients come in contact all primaries, get their prepare. Okay. So primary is now in the latest stage. So there wouldn't be any opcalls to replicating the same machine for executing this request. Sorry. So then primary start this process of changing the reconfiguration, okay, by sending this start epoch or these packets to the new replicas. Then it updates the states with the new epoch number and fetch a state from old replicas update log to primary. So all the basically replicas inform the old replicas that the new epoch started. Okay, basically they are in a new setting that can be that just a new setting number. And so then the replica, after this stage, the replica C is ready to be removed from the system and D to be added to the system. So let me see what's. So basically, I mean, the thing is, I'm not showing all the basically back and forth messaging there, but that's the whole idea. Okay, you get the latest. Okay, you make sure that you have the basically you finish with this prepare and prepare. Okay, okay, you have all the operations committed. Okay, in all the replicas, you want to make sure you did this. You committed all the operations. You start, of course, accepting any new events or requests until you start completely new, let's say, epoch, and you remove the old one and add the new one. So again, the idea is if admin doesn't wait for reconfiguration to complete, okay, and decommissions all nodes, it may cause a failure in all groups. So of course, the admin also waits for the process to finish, okay, in order to avoid the issues. So you cannot just simply shut down a replica and receiving reply at the clients, okay. So in this example that we're saying, if you receive this one here, you cannot just start shutting down this and removing it from the system, because it can cause basically failures in all groups. So you must ensure committed request survives the reconfigurations. So for do that, you can have a new type of request or check epoch reports the current epochs for the clients to make sure exactly at what configuration number you are at the moment to make sure nothing happens. So it goes through normal request processing. Return indicates reconfiguration is completed. Then in that case, in that situation, it's safe to remove the old replica and add the new replica. So I believe I went very fast here, okay, but I mean, I don't want you to get confused. Very straightforward. Okay, you won't even get confused by the name. It's, as I mentioned, you wanna make sure the old basically set of replicas have the latest commit. You stop receiving any new event, no new events, okay, till you completely remove the old replica and add the new replica. And you want to make sure that the latest basically state is existed in the new configuration, and which is for sure it happens. So what's useful when, let's summarize this. So do you need a backup fail or has network connectivity problem? Minority partition from the primary. In that case, quorum allows primary to continue without an issue. If primary fails or have network connectivity problem or majority partition from the primary, then you can rapidly execute a view change and switch to a new view totally with a new primary. And if a replica permanently fails or removed, okay, or if a new replica added, you administrator initiate reconfiguration protocol. So what we're talking here, the quorums allows primary to continue because you are making sure that the state is always in, basically you have the latest state always. If the primary itself fails, you do the view change, either centralized or decentralized way. And if you want to add a new replica, okay, you do the reconfiguration protocol. That's a summary of what we discussed today. Any questions?
I only have one.
Okay, go ahead.
Are the views reusable, or the replicas never go back to an old view?
No, you can actually. As we mentioned, the views are based. Let me go to the centralized or decentralized. If decentralized is this one, right? So you have three replicas, three view in the view one. Replica one is the primary, view to replica 2, view to replica 3. So if you want to switch between these three views, you can use, and it's the same basically in the view server in decentralized base too.
Yeah.
In decentralized base, we were saying you can view assigning the view numbers. You may basically keep adding that view numbers, doesn't matter. But in this case, yeah, of course, it's always switching, right? If a primary fails, you move to another one. Or even it can be a load balancing act. It doesn't matter even if they don't fail, you keep basically rotating between different primaries.
Yeah, okay, thanks.
No problem. Any other question? Okay, I know it was a little bit fast today. Maybe some of them sounds confusing, but I think it was the easiest things for this class. Because all the things that you need to know, okay, is summarized here. If the backups fail, you have the quorum. If the primary fails, you switch the views. And if you add or you change your configuration, you do the reconfiguration protocol. That's it. Like 10-second summary of the class. So if there's no questions, we're done with today's class. Just remember, next week is not a project presentation. We're going to continue. We're going to have 2 student presentation about taxes and RAF. It would be great if you read the papers because and read the both of them because it's going to help you understand them much better. And they are really, really famous. Raft especially is a very famous protocol, and you need to know that pretty well. Okay. So next week, remember, we're going to have two group student presentation. Okay. Okay, guys, have a good night. Sorry for being super fast. Okay.
Thank you, Maddie.
Hi.
Okay, guys.
Okay.
Don't forget the paper's title. You can check it tomorrow, and it will be ready to edit.
There's a link. I cannot find it.
The link, I'm sending it here in chat. Just make sure you can open it.
Yeah, it's in the announcements.
Just,
Is it?
just one thing, I think it's read-only mode.
Yeah. I said I'm going to fix it. I'm going to give you the permission to write this this particular sheet. You add your papers, and this is the link in the chat. I think you can open it there. Yep, I can see it's working. So take care, guys. See you next week.
Thanks.
Thank you.
Bye.
Maddie.
Bye.
Take care.
Thank you, Maddie.
Thank you.
Bye.
Thank you.
Take care.
Thank you.
Evening, bye.